we discuss comparison of two circular flows, we always tend to think that if the flow is circular, then there is always rotation. It's not necessarily so, and as we see here in a very simple example. Let us first see the components of fluid motion or velocity field in circular fluid field. So if the body is a solid body rotation, if in a circular motion, let us say in a cylinder, the whole fluid is moving or is rotating, then the radial component is zero, no motion in the radial direction, because the whole body is moving and it's moving just like with the same rotational speed as that of the cylinder itself. But u theta, the angular velocity, will be omega r. And if there is a rotation, but fluid is moving only on the axis and nothing else away from the axis, in that case, it's represented by ur is equal to 0 and u theta is equal to some constant k over r, where r is the radius. And similarly, for solid body rotation component, because whenever we talk about rotation and we consider the velocity components, we need to take into account vorticity vectors also and its values, mathematical computation. They are interrelated. They are important parameters to describe rotating fluid flow. So solid body rotation zeta will be equal to 1 over r, partial derivative of omega r square with respect to r, and that turns out to be 2 omega k. That is, its value will be 2 omega in the k direction. And if it is line direction, then there is no vorticity. You can see zeta is equal to 0 altogether. And this is also reflected in this simple diagram. When the body is moving, the fluid flow is moving as a solid body, everything is moving, then in that case, you can see that the velocity, how the velocity profile is changing. It's changing as with respect to theta. But when, and that depends on omega r. So as r increases, the value of angular velocity also increases. So that will be the value, and it's a solid body rotation. But then in the r direction, there is no motion. There is no fluid flow. So you can see here the particles represented in the circles, and they are showing that as they move from the center line, then their position is being changed due to rotation, and that rotation is reflected in different description of or different picture of the particles as they are represented in flow field A. When it comes to flow field B, and there the motion is only along the axis, but no motion away from the axial line, then in that case, the fluid is described as K over R. And K over R, this fluid is only moving in the theta direction. And there you can see that it depends on R. If R is small, the value of theta is relatively larger. And if R is large, then the fluid flow, then the rotation is almost negligible, and at substantial large distance, this will turn out to be almost equal to 0. And that is why in the fluid field B, we say that it is irrotational everywhere except at the origin, but away from the origin, it tends to be becoming small and becoming zero because R is dividing some constant K, and so a large R will reduce this term to be zero. Its analogy can also be seen in a roundabout flow on a wheel where the children are moving, and if this is rotating, then you can see that these children or the childs that are on this wheel, they will be rotating with the same velocity with which that wheel is rotating. So it's very much similar to solid body rotation. They will have the same rotational speed or velocity that the wheel will have. But in another picture, what we call as famous Ferris wheel, it's rotating in a circular direction, and therefore the people sitting in the chairs that are hanging from the top, they retain their position, and so they don't rotate, they only move in a horizontal direction, but no rotation is introduced in their motion, and therefore their motion remains as non-circular or irrotational.